Hello, welcome back. Today we're going to continue. Well, how's everybody? I hope you're all doing well. We do have our assignment 3 released on Blackboard. So make sure you start working on your assignment 3. The first part is Minhash and LSH. You should be able to do it right now. For the second part is building a recommendation system. And you will be able to do that after we finish our recommendation lecture next week. Also, if you look at the syllabus, you do have extra time to work on assignment 3, but make sure you start early. Like I said before, this is the most challenging assignment. And before your assignment 3 is due, we are going to release your assignment 4. So if you finish your assignment 3 early, you can start on your assignment 4. All right, so great. Still remember what we talked about last time? we work on this algorithm called TF-IDF, right? So what is our goal here for TF-IDF? We are building a content-based recommendation system, right? And we are building a content-based recommendation system. The items that we want to recommend are documents, right? So someone said find similar topics, right? So you want to recommend documents with similar topics to your user. And TF-IDF is a really cool algorithm that will be able to help you generate topic words. So when we look at TF, just a quick recap. When we look at TF, this is a term frequency, how often that specific word is mentioned in a document J, right? So when we talk about TF, it's always document and word. IDF is about how many times this word appear in a repository, right? So the goal to include IDF is to penalize the very popular words. If a word appear in many documents, it's not very useful. So to use TF-IDF to compare document similarity, we take high TF-IDF words like last time we did it on the whiteboard. You can use a threshold, you can pick top keywords and all that. So in this case, on your slides, they're saying that vector has 1 if word is in the set for that document, 0 if it is not, right? Remember, you can keep the original TF-IDF scores in the feature vector to describe each document, or you can use 1 or 0. Between two documents, only a finite number of words among the two sets. So almost all components are 0, do not affect the dot product. And here just to tell you where we can use cosine similarity to compute the similarity between two documents once you have their TF-IDF words, right? We covered this slide last time. So I think we also talk about this, but not on this slide. Document similarity, we have two kinds so far. So chapter 3, we talk about nearly identical documents. And nearly identical, we are talking about lexical similarity. This means documents are similar if they contain large fractions of identical sequence of characters, right? So these are plagiarism detection case. Speaking of plagiarism detection, we did identify some cases of plagiarism detection for your assignment 1. So I want to tell you this again. Please do work together. So you can work with other people, you can work with other students, you can either work with people who are not in this section, which is all fine. The only thing that you cannot do is to give other people your code or to copy from other people's code, right? It can be some code you find online or something. Don't do that. So let me give you one example. I see this over all the years. Your best friend or some friend you met in class will tell you that, please share your code with me. I promise you I will not copy it. Or I promise you I just need to know some functions and I'll write my own. That is not okay. Okay, so even if this person will not copy your code, you cannot share your code with this person. Okay, so please do not share your code. Okay, so all the machine learning data mining techniques these days are really good. So even if they copy your code, change the name of variables, merge functions, we still detect them. So please do not do it. Do not share your code with other people. Do not copy other people's code, but you should work with other people, okay? You can discuss and you can talk about algorithms. You can write pseudocode, not working code. All right, So lexical similarity, these are the things that we covered in chapter 3, right? 2 weeks ago or last week. We have shingles that can help you generate features. So instead of using shingles, this time we are using TF-IDF words, right? TF-IDF words can capture topics. Shingles just capture lexical similarity. And in chapter 3, we convert shingles to min hash functions and use locality sensitive hashing to help us process large document sets. And for recommendation systems, we do not want to use lexical similarity. So we are using TF-IDF to find components, to find topics that are important to distinguish one document from other documents. And this, after we identify this, we can use a distance measure, Jacquard, or cosine similarity to help us find similar documents for recommendation. And at the same time, you can still use min hash or locality sensitive hashing for finding similar documents. But in this case, all the algorithms we covered in class are based on Jacquard similarity for min hash and for LSH, okay? But you actually can find implementations for min hash and LSH that can take advantage of cosine distance. We used to have this as a part of the homework assignment, but this semester, I think you guys have enough. So we do not have this part. All right, so other options to describe item content. We can identify, obtain item profile features from some tagging systems that provided from users. So these are useful for content recommendation system for images, photos, Instagrams, Facebook images. Users enter words or phrases to describe them, like hashtags. Or you can use other types of metadata like GPS location, and these are usually very cool, right? You can do location recommendation, you can find interesting things about an image for a location, and you can use other data set for that location, like Google Maps, to add more content features to your items. We can use all these tags as a recommendation system. So for example, if user retrieves or bookmark pages with certain tags, then you recommend other pages with the same tags, right? Similar idea. In this case, you're treating all these tags as your TF-IDF words. Only works if users create tags or allow automatic geocoding, right? Some applications, this might be doable. So now we have talked about how you would create item profiles for a content-based recommendation system. So 2 ways, right? So the first way is you use metadata. I'm not very good at writing this, but metadata of an item. So this could be all these tags or some explicitly defined metadata of an item, price, colors, and all that. Or if you have documents, we can use TF-IDF words. So what have we learned so far? Well, we know how to look at all this metadata or TF-IDF words, and we know how to convert each item into data points with multiple dimensions, right? And we know how to compare them. We can use Jacquard distance or cosine similarity. But now, how do we really do the recommendation then? We know how to compare item similarity. What about users? So this time we are going to create user profiles. So general strategy for content-based recommendations. We construct these item profiles. We just talked about this already. Now we want to construct user profiles. So in this case, we also want to create a vector or vectors to represent users. And these vectors will have the same components, the same dimension that describe users' preference. So when we say the same components, we mean the same components as in the item profile. This way we can use cosine similarity or Jacquard distance to compare them. So let's look at some examples for user profiles. To construct user profiles, we create vectors with the same components that describe user's preference. Best estimate regarding which items are user like, it's some aggregation of the profiles of those items. Well, what does this mean? Okay, so this implies for a given user U, the user already tell you this user's preference for some items, okay? So maybe the user has purchased these 4 items, or the user has liked these 4 items. Then you look at the item profile of these 4 items and trying to figure out a way to aggregate these 4 items profiles and generate a user profile, okay? So you are not creating user profile from scratch. You are taking items, all these items that somehow are related to the user preference and merge them and create one user profile. So many ways that you can do this, some possibilities. If you have Boolean vector for your items, the average components of vectors representing the item profiles in which the utility matrix has one to the use. This is a very long sentence, but it's actually very simple. So say for items, you have movies, okay? So if your movies are described in an item vector with actors. So you have actor 1, actor 2, actor 3, and so on. Okay, so if you have 5 movies, you have 0, 1, 1, 0, and so on. So 0 means movie 1 does not have actor 1. 1 means movie 2 have actor 1, and so on, right? So if users already show that they like these 5 movies, for each component here, you can look at how many of them contains 1. So if many of them contains 1, that means this user likes movies, prefer movies that have actor 1, okay? So that's here. This is saying that 20% of the movies that user likes will have actor A. Then the user profile for that user A component will become 0.2, right? For let's say this actor, if every movie has this actor, then the user component for this actor will be 1, right? So then you can easily see that the user profile will have the same length as the item profile. And all these numbers are just some aggregated number from your item profiles. So this is for Boolean utility matrix. For a non-Boolean utility matrix, so still remember what's a utility matrix? A utility matrix, the easiest way to think about this is you have users here and you have items here, right? And you have ratings. So for Boolean one, we already talked about it. For non-Boolean ones, this could be ratings. And for the non-Boolean ones, we want to weight the item profiles or the vectors that represent the item profiles by some rating values. So how do we do this? Let's say user U gives an average rating of 3, and user U rated 3 movies with actor A, and the ratings are 3, 4, 5 for these 3 movies. We want to normalize these ratings by subtract the user's average rating, so it becomes 0, 1, 2, right? 3 minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2. Then this user profile component for actor A will be value of 1. That means if you look at here, the movies that have actor A receive these ratings. And the average rating for a movie that contain the average rating for movies that contain actor A would be what? 0 plus 1 plus 2 divided by 3, so that will be 1. So right, super easy, right? So you just need to find a way to aggregate these numbers, and these are all pretty straightforward methods. there is no fixed method that you should use. It all depends on either how you design your Boolean, either how you design your item profiles, utility metrics, or it depends on your application. You won't always take a small sample and test them, test various methods to see which one works best. Negative values here, negative weights here will be below average ratings. Positive will be for above average, right? Because A now have a value of 1, it's better than 0. But 0 means what? Neutral. That means the movie will have the same, the actor carries the same rating as the average rating of 3. But 1 is larger than 0, so it's better than the average. So now we have user profiles, the prediction heuristics that given user profile X, some item profile I, we want to estimate the degree to which that user X would prefer an item by computing the cosine distance between X and I, right? So pretty easy. You take all the items, these are all the items. In every item, you will have a feature vector, right? So this is your feature vector. Then once you can compute a user profile X, you just compute the cosine similarity between X and every item here. Then you find the one that's most similar to X. So that's a very common method. Other method that you can do is using machine learning methods. So using machine learning method, you will take the given data set as training data. For each user, you build a classifier in a supervised way to predict the rating of all items. And you can do a categorical prediction. So scale of 1 to K, you can map to K classes, right? So you can say, all right, I have a user, and for this user, I don't really want to build user profile. The only thing that I want to train my machine learning model with is I know that all these items are the ones that the user likes. So I will throw it into a machine learning model, could be random forest, could be decision tree, nearest neighbor, to see if the model would be able to, based on this as training data, to tell me what would be the user preference for this new item that the user has not created before. So that's this. But in general, this method will require your user to leave many ratings because to train a machine learning model, you need to have large amount of training data. And there are many different types of classifier you can use: naive Bayes, k-nearest neighbor, decision tree, neural networks, and we're going to talk about decision trees. So let's look at one example. Say we want to build user profiles in the previous example. User gives ratings of 3, and we normalize it and do all kinds of stuff like we said on the last slides. So in this case, once now we have user profiles as a feature vector. Now we start to compare this user profile feature vector with all the item profile feature vectors. For movies with many actors that the user likes, your cosine of angle will be large positive fraction. Remember cosine similarity. Let's say this is your user profile vector. And if the movie has many actors the user like, we expect that the movie will have some vector like this, right? In very similar direction as the user profile. And this means we will need to have a large positive fraction of your cosine of angles, because large cosine of angles, after you apply arc cosine, you are going to have a small cosine distance, so small angle between them. So we need to have large positive fractions. And if you look at the heuristic here, movies with many actors that the user like, So that means if we look at that means if we look at something like, let's say the user likes, this is user, and the user has 3 components, 1, 0, 0. Each component represent an actor. So this is actor 0, actor 1, actor 2. Okay. And when you look at movies, 0, this movie has actor 1, 1, 1. This means this movie has all 3 actors. Movie 1 has 0, 0, 1. Movie 3 has 0, 1, 1. Okay. If you look at this, let's just make this 0.5. If you look at this, when you are trying to work on your cosine similarity, remember the number, the top part in your cosine similarity formula, you're doing a dot product, right? So you'll be 1 times 1, 0.5 times 1, 0 times 1. So how do we make this dot product to have a large positive fraction? Large positive fraction, so we can have a small angle. That means if you have a positive number in the user profile, you should also have a positive number in the item profile, right? If you have a negative value here, let's say this is minus 0.5, you want to have a 0 here, right? Because if you have a 1, eventually the dot product will sum this up and you are going to have a smaller number. So the movies with many actors that the user like. So user like means you have a positive value here, and many actors means you have a 1 here, and this is good. This will help you to get a large positive fraction and small angle. Movies with a mix of actors that the user likes and doesn't like. So you will have some positive numbers here, some negative number here, and eventually they might cancel out. If they cancel out, the cosine of angle will be around 0. That means the degree between these 2 vectors would be close to 90 degrees, right? So vector, user vector, 90 degree means neutral. 180 means completely different. So a movie with many actors that the user doesn't like, the cosine will be a large negative fraction. And this will be large cosine distance between 2 vectors because the angle becomes large. So I hope this is clear. Recommending items based on the cosine distance, we can estimate degrees to which a user would prefer an item by computing the cosine distance between user vector x and all the item vectors. We can scale the components with the values that are not Boolean, like what we did on the previous slides. So you normalize the review ratings so that average will be 0, and above average will have a positive value, below average will have a negative value. Then you can use LSH, MinHash, or random hyperplanes. This is very similar to LSH, but we didn't cover it in the class, to help us identify similar items to a user, right? It says place it in the bucket. That means they could be very similar. For a given user, we apply these techniques to identify in which buckets we look for items that might have a small cosine distance from users, right? So this is exactly like what we did in that finding similar document lecture. The last part, you have LSH, you have MinHash. Now you want to use them to help you find similar document. But in this case, you're not finding similar document. Your input now is a user. You are finding the most similar items to that user. So that's everything about content-based recommendation system. So let's look at decision tree. If we don't want to use cosine similarity, what would be our choices? And would that be a good choice? Decision trees. Say your items are news articles, your features for each item are high TF-IDF words, exactly like what we did before, maybe top keywords. Suppose you're a user you like articles about baseball, except articles about the New York Yankees. The role of the utility metrics for the user you will have a 1 if the user has read that article. It will have a blank otherwise. So now we can use this utility metrics to train a decision tree. And this decision tree will be specifically trained for this user you, which means you cannot reuse this one for a different user. Okay. In the decision tree, the decision tree algorithm will select a predicate for each node and split and start to grow the tree. I will show you on the next slide. And when the new item comes in, or when you want to classify a new item to see if the user would like it, you will start at the tree root and apply all the node predicate to the item. If the predicate is true, go to the left, false, go to the right. You repeat until you reach a leaf node. So this looks complicated, but it's actually very easy. So this is an example model that someone trained for that user. So each node here, this is a decision tree. Each node here is a predicate. So the first node says, does the article contains the word home run or better or and pitcher? Okay. So if not, then the user will not like it. Great, because we know the user likes baseball. If it is, we need to further check if the article contains anything that's about Yankees, the Yankees. If it does, we say the user will not like it. If it doesn't, we say the user will like it, right? So this is very cool. One thing about the decision tree is it's explainable. So you will be able to tell the user why I predict that you will not like this article. Well, you can just look at the predicate. But the weakness of this approach is classifiers of all types will take a long time to construct, so to train. For decision trees, you will need one tree per user. You cannot generalize this. Construct a tree requires the algorithm to look at all item profiles, the profiles of every item, have to consider many different types of predicates, right? Like on the previous slides, we talk about this very simple predicates, but you can actually have more than that. It could involve complex combinations of features, and it can be very complex so that you cannot really explain it. Typically only apply to small problem size, but generally can have better result than cosine similarity if you have large training data, okay? But this is more on the machine learning side, not data mining. Remember, we talk about machine learning usually work on models and with smaller data sets than data mining problems. So in summary, the pros for a content-based approach: first, you do not need data on other users. You can only work, you can take one user's previous records and just work on it. There's no cold start problem for items. That means when a new item comes in, you can already start to compute its similarity to other items. You do not have the sparsity problems. New items can receive recommendations. It's able to recommend to users with unique taste, because every user can have very different taste, and you construct the user profile from all the items they like. So it doesn't really matter if the user has a unique taste, you can still find recommendations. It's able to recommend new and unpopular items. And again, we can recommend new items because we do not have cold start problem. Unpopular items because we can overcome the sparsity problem. The unpopular items, as long as we can describe it, we can recommend it. So no first rater problem, new product. Well, that's the problem, that new product never have been rated and we cannot recommend it. So we do not have this problem. able to provide explanations. You can provide explanations by saying, hey, these are the content features we think that are important to you so that we recommend these items, right? That's pretty common when you look at some of the applications. It will say, oh, we recommend you this item because you purchased the other item before. So some weakness for the content-based approach: finding appropriate features is difficult. Movies, images, music, there is no good way to identify features for them for a specific content-based recommendation system. Recommendations for new users are difficult because you do not have any information that you can use to create the user profile. Over specialization, that means you would never recommend items outside users' content profile. This is sometimes really bad, right? You are not really exploring, helping the user to explore the huge item database you have. You always concentrate on the user's past histories. People might have multiple interests. So if you look at people's past records and you try to combine them all together, you are looking at one interest. A good example here is, I don't know if you guys are using Netflix. So originally, Netflix will not ask you to create profile. But now Netflix encourage people, well, not encourage, they have these plans that you can share your Netflix subscription to other people. They start to create all these profiles. And when you start to watch, you can click on your profile to indicate this is me. But you don't want to share your Netflix account with someone. Okay, say, let's say you like Korean drama, okay, and you don't have kids, and you're sharing your Netflix account with your brother, and your brother has two young kids. They love watch cartoons and all these kids-friendly shows. If you mix these two profiles together, that would be a disaster, right? Netflix will start to recommend many kids shows to you and you don't care. It might recommend some Korean dramas that are not okay for the kids to watch to your brothers. So it's the same here, that people might have multiple interests. So content-based recommendation system does not work very well. You need to have other ways to separate all this interest. Unable to exploit the judgment of other users. That means we do not use other people's rating. And this is not very good. And I'm going to show you the approaches that can handle this and use this in doing a recommendation next. All right, any questions? Okay, so if you don't have any questions, let me switch to next set of slides. But before I do that, I want to upload the slides. So just bear with me a second. Okay, you should be able to see the second set of the recommendation system slides on Piazza. All right, so second topic in a recommendation system called collaborative filtering. It's called collaborative filtering. So we cover a content-based system. And this is perhaps the most commonly used recommendation system in practice, which is called collaborative filtering. We talk about content-based, and we say that one of the major difficulties or challenges in building a content-based system is you need to come up with a way to describe your items, right? But for collaborative filtering, you do not need that. Oh, sorry. In collaborative filtering, we build a model from a user's past behavior again, but we look at similar decisions made by other users. So this way, we do not really care about the item content, and we can still make a recommendation. Then we use this model to predict items that user may like. And the collaborative way is the suggestion not made to a user utilized the information across the entire user base. Okay, and there are multiple ways to do collaborative filtering, and we are going to cover them all. So let me show you one example. User-based collaborative filtering, consider user X. This is your user X. User X find a set of n other users whose ratings are similar to X rating. So user X has some preference. The entire user base for each user, you have some preference, and these are similar. This set of users prefer some item, and you can take this item and recommend it to X, right? The idea is very, very simple and very straightforward. Let me just give you one example. Say you have you are looking for a location that you want to purchase a house, okay? And there are 10 neighborhoods you are looking at. If we are going to build a content-based recommendation system to recommend a neighborhood to you, what do we need to do? Well, we need to create an item profile for each house. We will need to say, all right, in this neighborhood, you have this house, and this is the price, this is the number of rooms, and all that. But people have very different preference of a neighborhood. So you will need to add more attributes or more feature vector components to describe a neighborhood. It can be safety, school ratings, median housing price, lots of them, right? Then the user will be able to click on some items to say, oh, I like all these items. Then you generate a user profile, then you recommend neighborhood. A user-based collaborative filtering approach is that user comes in and you say, hey, so let's assume I'm the user. I'm looking at this 10 neighborhood. I have no idea about this neighborhood, but I do have some friends already live in the city. So let's say I have 100 friends living in this 10 neighborhood. I just find that friends that have similar taste to me, and I'll just move to that neighborhood, right? So maybe some of my friends really like hiking, really like to go into restaurants. So that person or those people will live in a neighborhood that will support those type of activities. So I don't care about the neighborhood content, but I care about the people who would have similar taste to me. Or for another example, if you have two groups of students, one group of the students wants to pursue PhD. The other group wants to go to the industry after they graduate with a master's degree. So somehow this group of students, when they start to choose courses to take or their research activities will be very different, right? So instead of looking at each course to see which one you want to take, you identify yourself as in either one of this group, then you just see what other people in that group do, and you just do it, right? To do that, we call this collaborative filtering because you are looking at only your preference and other people's preference. Then you can start to do recommendations. So collaborative filtering works by collecting user feedback. So rating for items, this is important. You collect feedback. You do not generate characteristics to describe items. We want to exploit the similarity in rating behaviors among users to determine the recommendations. There are two types of CF algorithms, neighborhood-based, or we call it memory-based, and the model-based. So I think we are going to cover this next week, and hopefully we will be able to cover both types of neighborhood-based algorithms today. And I will tell you why this is called neighborhood or memory-based algorithms. All right, so neighborhood-based algorithms. First type, user-based algorithm. Okay, so before we talk about this, let's take a 10 minutes break, come back at 7 p.m. If you have any questions, feel free to leave it in the chat. I will answer them when I come back. All right, I'm back. Okay, so user-based collaborative filtering. This is called neighborhood and memory-based for a reason, and the reason will be clear on this slide. Say you have an active user, you have a user that you want to make prediction for. And let me see, chat. In the user-based collaborative filtering, we want to find a subset of other users based on their similarity to the active user, right? You want to find a subset of the other users that are most similar to this active user. Then you just do a weighted combination of their ratings to make the prediction for the active user. So here are the steps. You assign a weight to all users with respect to their similarity to the active user, right? Let's say you have 100 users. You have an active user. You compare this active user to this everyone in these 100 users, you find the most similar ones. And that similarity is defined by a weight. You select K users that have the highest similarity with the active user, and these K users are called the neighborhood. So that's why it's called the neighborhood-based approach. And because we are using a neighborhood, so it does not consume lots of memory, and it's also called memory-based collaborative filtering. Based on the K users, you will be able to compute a prediction from a weighted combination of the selected neighbors' rating, and you are done. So very simple. Let's look at a couple examples. Similarity between users, but as usual, we need to be able to define this similarity. And the similarity, we are going to use W weight to represent it. So weight between user X and user Y. This weight is measure of similarity between user X and the active user Y. Let's say Rx is the vector of user X rating for all the items you have. Possible similarity metrics that you can use to measure the similarity between user X and user Y would be Jacquard similarity and cosine similarity. So very well, just like what we did before for Jacquard similarity, works on sets. You don't use non-Boolean values. If you have ratings, you have to convert them into Boolean values. Cosine similarity will treat ratings as vectors, and then you compute their cosine similarity by looking at the angles. So X and Y as point and X and Y as sets are different. These are actually a bit difficult to understand, but it's just telling you that for your active user Y and the other user X, if you look at their ratings 1, 4, 5, this would be a set. And you cannot just use all these ratings. You can probably say, let's say this is for item 1, item 4, and item 5, right? And let's say if you have 10 items, 1, 2, 3, 4, 5 to 10. Then item 1 here, this is X user, this is Y user. Item 1 here will be have a 1, 1. Item 4, you have a 1, but 0 for Y. Item 5, you have 1 and 0. Oh, sorry, this one is also 1 because user Y has a 4. Item 3, you have a 0 and you have a 1. Then you do your Jacquard similarity. Cosine similarity, you can just look at this as ratings for each item. And assuming here you have 5 items, and you just compute their angle. And you're done. Okay, and the part as how you would choose which one, it really depends on your application. But you can see very easily here in the Jacquard similarity, we are ignoring all the ratings. But in cosine similarity, rating 1 and rating 3, rating 2 are all different and used in generating the cosine similarity because you have a dot product and a length here, right? In Jakarta similarity, whatever you rated 1 or rated 3, you will always get a 1. Okay, so Jakarta similarity did ignore some of the information, but sometimes it's very useful. All right, Jakarta similarity, we talked about this before, is the intersection between two sets divided by the union of the two sets, and Jakarta distance is just 1 minus Jakarta similarity. It's just a different way to look at the similarity measurement. Your old friend again, intersection is 3, union is 1, 2, 3, 4, 5, 6, 7, 8. So it's 3 over 8. Jakarta distance is 5 over 8. That means their distance, because the maximum distance will be 1, which means the two items are different, very different. All right, so how well does all this metrics works? Let's look at the utility metrics. Here are all your users, and you have your movies here, and you have all the ratings here. Intuitively, if you just look at ABC, we want to have AB to be more similar than AC. Why is that? Anybody? Did I lost everyone? No, we still have 22 people. 21. Okay. All right. So Bui says more common items. Jun says cosine similarity, but even without talking about similarity measurement, this is our chance to look at the data to decide what measurement we want to use, right? And say in our application, we want AB to be more similar than AC. So why is that? If you look at AB, they both rated Harry Potter 1 and what else? Nothing, only Harry Potter 1. So this is the only information we know, and they rated pretty hardly, right? The numbers are close. The ratings are close. If you look at AC, what are the information we have? Well, Twilight, and Star Wars 1. If you look at the ratings, it's pretty different, right? A likes Twilight, Star Wars 1. C doesn't like Twilight and like Star Wars, right? So they have very different taste. So intuitively, this is what we want. And let's try different similarity metrics to see which one will be able to give us the result that we want. All right, so Jakarta similarity will ignore values, ignore ratings in the matrix, only look at which items are rated in the matrix. That means the Jakarta similarity only care about what user has rated what movies, not the rating itself. So intersection over union between AB is 1 over 5. So while 1 over 5, okay, intersection is 1, and the union is 1, 2, 3, 4, 5. Okay, great. Similarity between A and C will be the intersection. Twilight, Star Wars 1, so 2. And the union is 1, 2, 3, and 4. So 2 over 4. In this case, if we are using Jakarta similarity between AC is actually larger than the similarity between AB. So what happened? This is not what we want. And we derive this result because we ignore the ratings, right? So in this case, we do not ignore the rating. So how do we do this? We can use cosine similarity. Let's look at cosine similarity. In working on cosine similarity, let's say we want to compute the cosine similarity between A and B. Remember, you are going to have a dot product. So this is the dot product here. And to do dot product, we just do 4 times 5 plus 0 times 5, because A did not rate Harry Potter 2, so we give it a 0. We treat blanks at 0 values, and we're going to talk about this later. And 0 times 4, 5 times 0, 1 times 0, 0 times 0, 0 times 0. So you only have 4 times 5. Then you calculate the length for A, length for B, and this is your similarity. And you do the same for A and C, your cosine similarity is 0.322. So let's look at A and C. When you do the dot product, you're going to have what? 4 times 0, 0 times 0, 0 times 0, 5 times 2, 1 times 4, 0 times 5, and so on, okay? And in this case, 0.38 is larger than 0.32. This tells us that AB is slightly more similar than AC. Great, so this is what we want, but it's only slightly. In this case, Jaccard similarity is better than the Jaccard similarity. However, we need to figure out a good way to handle missing data or non-rated items. So in this case, the way we can handle non-rated item is we can normalize all the ratings. We subtract the average ratings of a user from each rating. In this case, your low ratings will be negative numbers, right? It's below average. High ratings will be higher than the average, will be positive numbers. And 0 means neutral. And let's look at average rating for each user. Why do we have 10 over 3?
Because 4 plus 5 plus 1 and divide by 3.
Right, great, thank you. And you do the same for calculating the average rating for B, and for C and D, you have your average rating. Then you take your original rating, subtract it by the average rating, you have this. Then you calculate your cosine similarity. In this case, AB is a positive number. AC now becomes a negative number, means they are different. These two are very different. And this will be 85 degrees larger than 124 degrees. So AB is much similar than AC. Okay, so what happened? How come we just do a normalization and suddenly it changed the value? And why would this work? Think about this. What does 0 represent in the original matrix, and what does 0 represent in the normalized matrix? Anybody?
I think first one, 0 means there's no ratings. And the second one, 0 means the average score.
Well, wait. Both times 0 means no ratings. But here, the normalized utility matrix, 0 means neutral, right? It's average score. If we never rate it, we just give it a neutral number. But in the original matrix, 0 means what? Is it still neutral? It's actually not neutral, right? It's a number that's lower than 1. So that means the user even give it, if it's a blank, it's a rating that's even worse than 1. So this is not okay, because when if the user didn't rate it, it doesn't really mean the user doesn't like it. It could be the user haven't rated it yet. So usually your normalized cosine similarity will be able to give you a better result like this one. And speaking of normalized cosine similarity, we have to talk about Pearson correlation. So Pearson correlation is actually the most commonly used measure of similarity for building a recommendation system. Very often you can see people try to use either Pearson correlation or cosine similarity and try with a small data set to see which measurement makes more sense for their data set. I'm going to show you a link later that you can see how people test it in their real data application. So Pearson correlation measures the extent to which two variables are linearly related. This sounds really difficult to understand if you don't understand Pearson correlation, but we have a slides. We have an example on the next slides that you can look at. But let's just look at this function. What are these? Well, for user U and V, if we want to calculate their Pearson correlation, we just take all the ratings from user U for a specific item, subtract that rating by the average rating of that specific user U, and we do the same for V, and we do a dot product. And this is the length of user U's rating, the length of user V's rating, but again, you normalize them. Right, so this looks exactly like what we did before with a normalized cosine similarity. So what does this tell us then? Well, Pearson correlation help us to identify the linear relationship between two variables. And if we put them on a chart, it looks like this. So two variables, say this is hiking, this is skiing, right? If you collect many data points, say this is user 1, this is user 2, this is user 3, and if their point pattern looks like this they're on a straight line with this type of slope, you have p equal to -1. They are negatively related. If you have something like this, the slope is negative, but they are not exactly on a straight line, so your p will be larger than -1, but smaller than 0. Something like this would be 0, means there's no linear correlation. +1 will be like this, they're on a straight line with a positive slope. This will be between 0 and +1. So the minimum number of Pearson correlation is -1. Maximum number is +1. No relation will be 0. And if you look at this Wikipedia charts, it actually provides you more information, more examples. 1, 0.8, and you start to deviate from this straight line, so 0.4, 0, there's no clear straight line, -0.4 because your slope is different, and so on. Okay, so this is Pearson correlation. This is just a different way to measure the similarity between two feature vectors. So if we look at Pearson correlation, a Pearson correlation example, this is your utility metrics, users, items, and ratings. This is your Pearson correlation formula, which you don't have to remember, but if you don't remember, I don't think you can understand the algorithm without remembering this, because it's very easy, right? Dot product, but normalized value, and length, normalized value, and that's it. So let's say we want to find the correlation between user 1 and user 5, and we call this the weight of 1, 5, right? The similarity between user 1 and user 5. The set I of correlated movies are I1, I3, and I4. So let's look at it. I1, I3, and I4. I1, I3, and I4. So one thing I should mention, the difference between Pearson correlation and your cosine similarity, even the normalized one, is Pearson correlation only look at the correlated ones. So if you have a blank, we will not use it. So you see, every item we are marking here has two ratings, one from user 1, the other one from user 5. For user 1, the average rating on correlated movie is 14/3. For user 5 is 10/3. So let's look at 14/3. So 4 plus 5 plus 5 is 14. Oh, awesome. 10 will be 2 plus 1 plus 3 plus 5. Wait, for user 5, this is wrong. Okay, yeah, sorry, you don't use 1. Yeah, I know this is elementary school math, but this is the 3rd hour I'm teaching today, so. All right, 2 plus 3 plus 5 is 10. Thank you. Now we are calculating the Pearson correlation, and you start to take 4, right? 4 is here, normalize it, and you want to do dot product. So what is your corresponding component? This 2, normalize it. What's the next component? 3, you take 5, 5, normalize it. You take 3, 3, normalize it. What else? 4, 5, normalize it. 5, normalize it. Okay, great. So you have the number. Number is this part, right? Your dot product after you normalize them. The denominator, you take a square root of, again, the same number here. And this is here. And this is here. This is here. Oh, no, sorry, this one. Right, you just calculate the length of each vector after you normalize them. So you have the denominator. And this way, the Pearson correlation between 1 and 5 is 0.756. Good. So this is another way to measure the similarity between feature vectors. In this case, the feature vector represent a user, and the content of the user vector are ratings of that user. So let's make a user-based prediction with the Pearson correlation. The way we can do the prediction is to do a weighted sum of other users' weighting. So just look at the equation here. It's very easy to understand. This is telling you your active users rating for item I, okay? You want to predict this rating. And this prediction is equal to the average rating that user A has made plus ratings from a set of users that are similar to your active user. This is the set of users who are similar to your user minus that particular user's rating average. So this is the normalization part times that weight you calculated with Pearson correlation, right? This is the Pearson correlation between user A and user U. Then divided by the summation of all the weight, right? So this is just a weighted average. And because here you are doing normalization, that's why at the end you want to add that average back for predicting the rating for user A on item I. So when making all these predictions, we want to calculate average for all rated items for user A and U. The summation is over all users who rated I. If we look at an example, say we want to predict ratings for user U1, where's U1? U1 for item 2. And in this case, what are the users we want to use? Well, assuming that we are not doing a neighborhood-based approach, we want to find all users. In this case, because we don't really have that many users, in this case, we can find all the users that has rated item 2. And let's say we use a similarity of U1 to all these users. So the weight between 1 and 5 based on our Pearson correlation is this number. 1 and 4 is this number. 1 and 2 is this number. Okay, so assuming that you know how to do Pearson correlation. Why aren't we including user 3? Anyone? user 3 did not rated item 2, right? So we do not know user 3's preference to item 2, even when, let's say, even when user 3 is very, very similar to user 1, you still cannot use this as a recommendation because you do not know user 3's preference of item 2. Okay, so Pearson correlation, you calculate these 3 numbers. Very important thing to know. Don't get confused by Pearson correlation, cosine similarity, and Jaccard distance, okay? These are just measurements or definition of similarities between two users. You can use all kinds of methods to define this. And Pearson correlation, we are introduced it here just because it's popular and in practice, it's very useful. It shows great performance. You just need to know that you are able to calculate a weight between two users, and this represents their similarity of rating behaviors. Okay, so you have 3 numbers here. So to predict user 1's rating for item 2, you first take the average rating of user 1, and you start to do a weighted average. So how do we do weighted average? You take 2 minus 2.5. All right, so what is 2? What is 2.5? Okay, let's cheat sheet. 2.5 is 5 over 2. Okay, so 4 plus 1 is 5. 5 over 2 is 2.5. So that's this. This is the average rating for user 2, except item 2, because we are working on item 2. And 2 minus 2.5, this is the user 2's rating here. So this tells you how much does user 2 likes item 2, right? So this gives you a slightly negative number. What does it mean? Does it mean user 2 likes item 2 or doesn't like item 2 or really doesn't like item 2 or really like item 2? What does this tell you? Minus 0.5. What does this tell you guys? Somewhat dislike, right? So slightly dislike because it's a minus number. It's a negative number. And you have a minus 1 here. This is the similarity between user 1, right? That's your active user to your item, sorry, to your user 2. What does user 1, what does minus 1 mean? Does it mean that two users are very similar or very different? Very different. Great. All right, so let's look at the next one. 4 minus 2, sorry, 4 minus 4, what is this for? This is the rating for item 2 from user 4, right? This is this 4. And what is this for? This is the average rating of user 4 except item 2. So you only have 4, so 4. So 4 minus 4 is 0. That means user 4 has a neutral experience with this item. And the similarity between 1 and 4 is actually 0, means they are not similar and they are not dissimilar. So 0 times 0 is 0. The last one, 1. What is this one? User 5 rating on item 2. Great. 3.33. So 2 plus 3 plus 5 divided by 3 is 3.33. This is user 5's average rating, excluding item 2. This means user 5 likes item 2 or doesn't like item 2. Well, it's a minus 2.33. So user 5 must not really like item 2. Right, and if you look at this original matrix, you can see that user 5 actually rated others much higher than item 2. And 0.756 is the similarity between user 1 and user 5. So this is your weighted average, and because it's a weighted average, you have to divide it by the summation of all the weight. And you have this number. Awesome. This is the predicted rating for user 1, for user 1 and item 2. Okay, great. So in a neighborhood-based algorithm, we will choose a subset of the nearest neighbors of the active user to calculate that similarity. Then we will use this for prediction rather than all users who have rated them. So from here, you can see that when calculating the prediction, we are actually taking 3 users, right? But in practice, your user base will not just have 5 users. You probably have 1 million users. And once you calculated this Pearson correlation, you're going to remove the small ones, the negative numbers or small numbers. In this case, let's say we have a neighborhood of 1. We only care about the top similar users. Then you're going to remove this 2, and you're not going to use this. That means you only care about this user. Okay. If you only care about this user, you can see it's very interesting that this term canceled out. So you only have this. This is the normalized rating for user 5 on item 2, right? You take this normalized value, you add it back to this average rating of user 1, and you have the prediction. So that's the neighborhood-based approach. So all the things we have talked about so far are user-based CF, which means we are identifying the similarity between users and we use that similarity to help us make a prediction. The next topic I want to talk about is item-based collaborative filtering. So neighborhood-based algorithms do not scale very well when you apply to millions of users and items because of this computational complexity to search for similar users. Well, possible solutions is you can use this LSH or MinHash to help you speed up. But again, for one active user, you have to compare this user to all other users and find the most similar ones or top K similar ones. That's very time consuming. So in order to overcome this problem, I believe Amazon came up with this idea. It's called item-based collaborative filtering, so item-to-item comparison. Rather than matching similar users, this is matching users' rated items to similar items. So you compare items to find their similarity. And in practice, this usually gives you faster online systems, the system that you have to answer questions in real time, make recommendations in real time, and better recommendations. And this is usually because ratings for an item does not change very often because an item can have thousands of ratings. The ratings for a user can change pretty often, right? The user might not rate that many items. And if it has changed significantly, you have to recalculate the similarity again. But item to items vector is more stable and you can usually pre-calculate them. So similarities between pairs of items are computed offline and you can update them once in a while, but you don't have to update them very often. You predict ratings of user A on an item I based on a simple weighted average, again, like we did before. So let's look at this user item-based collaborative filtering. Say this is your utility matrix, this is your user, this is your item. Okay, great, user, items. Item-based similarity works as this. Let's say I am user 1. When I am looking at this item J, the system wants to be able to predict my rating for item J. Okay, this is a question mark, I don't know. But the system knows that I already rated item I. Based on my rating history and the rating history of item I and J, the system can first compute a similarity measurement, W, between I and J, right, based on all these ratings from the same user. And if these ratings are very consistent, say 5, 5, 1, 1, 2, 2, and so on, you know that these two items, I and j, are very similar. If the ratings are very different, say this one is 5, this one is 1, this one is 5, this one is 1, and so on, we know these are very different items. Okay, so basically you are calculating a weighted a weight to define the similarity between two items using their rating histories. Now, once I have that similarity, let's say if the similarity tells me that I and j are exactly the same, and I know that user 1 rated 5 for I, how would I rate j? If they're exactly the same, I will predict the user will rate it 5. If the similarity measurement tell me that I and j are completely different, and the user rated 5 for I will predict a rating of 1 for j for user 1. Okay, so it's that simple. But we are going to look at the algorithm and some examples. All right, again, we're going to use Pearson correlation between two items, item I and item j. The Pearson correlation between two items is calculated as follows. If you look at here, this is all the users that has rated both I and j, right? You have to have the users that rated both items, or you cannot really compare their ratings. You have the dot product here. Again, for a specific user U, note that you are looping through all the users. For a specific user U, this is the rating of user U on item I. You normalize it by item I's average rating times user U, the same user. This user U's rating on item J, because now you're comparing I and J, right? This weight is about I and J. And you normalize it again. This is the average rating of item J. And then here you compute the length, normalized length. So very similar to what we did before, is right now we are computing the similarity between two items instead of two users. Okay, so we're going to sum over the sets of users who rated both items, I and j. This is important, but this is important, but at the same time, if you don't have users now who rated both items, you will not be able to come up with these two components, right? So if your user only rated I, you will not have RUJ. This RUJ is rating of user U on item I, RIUI, and this RI is the average rating of the ith item by all these users. So how do you make a prediction? Let's say you want to predict ratings for user U on item I, and you have all the weights pre-calculated. This is the weight between item I and item N. RUN is this active user's previous rating history. This user has rated item N before, item N before, but not item I, right? The summation over a neighborhood sets of N items will be able to give you the prediction like this. So neighborhood N means you are looking for the top N items that are most similar to your item for prediction, in this case, which is item I. So look at this WIN. This is the similarity between your target item and all the items in your neighborhood, the most similar ones. And this is your user use rating on the most similar items, because you already have this data. Then you just normalize them based on this, the summation of the weight, because this is the weighted average. All right, cool. So this is everything you need to know about the item-based prediction. It's super easy, right? So you just compute the similarity between items, and you just do a weighted sum, and you have the result. But let's look at one example. Say item to item CF. Let's say our neighborhood is 2. This is your utility matrix. Now you have users here and you have movies here. Our goal is to be able to predict user 5's rating on movie 1. So great. If we want to predict this, what are the other items we can use? Well, what are the things we know about user 5? What are the things we know about user 5? We know, so we only know user 5's rating on 3, 4, 5, and 6, right? Movie 3, 4, 5, 6. And our goal is to predict 5 and movie 1. So what we can do is to find similarity between 1 and 3, 1 and 4, 1 and 5, and 1 and 6. And pick the top 2, because n equal to 2, pick the top 2 similar movies to this movie, and then make the prediction. So say we are able to generate all these similarity values. So these are made up numbers. Don't try to compute this, because this is not correct. Made up numbers just to facilitate this example. So W1J, the similarity between 1 and 1 and itself is 1. The similarity between 1 and 2 is minus 0.18, but we actually do not have to calculate this because you don't have a rating here. Sorry. Because you do not have a rating here, and these are all the ratings, all other ratings you have. And we are saying that neighborhood equal to 2, so we want to find the two most similar movies to movie 1. So who are the two most similar movies? You have 3 and you have 6, right? So we identify 3 and 6, and we have the similarity weight 0.41 and 0.59. And then we can easily do that weighted average. So 0.41 times 2, right? This is me, my rating on this movie 3, plus 0.59 times the rating of 3, which is here, and divided by the summation of the weightings. Then you have 2.6, and this is your number. Okay, so this is the similarity number you can, this is a prediction that you can calculate using item-to-item collaborative filtering. So if we look at another example here, and say this Wij is this, and we want to be able to find user 2's prediction for I2, what would be your set of view? Well, in this case, we are looking at item 2 for user 2, and we want to make the prediction by finding similar items to item 2, right? And all the similar items should be something that user 2 already rated. So in this case, we are looking at the set of users who rated both items. What would be the members of the set U for weight 1 and 2? Weight between 1 and 2. User 1, user 4, right? User 3 only rated this one. User 2 does not rate this one, so we can only use user 1 and user 4 to help us calculate this. All right, so that's it for today. We are going to continue on this next week, and I'm hosting the office hour right now. If you have any questions, please stay Make sure you work on your homework assignment. Please start your assignment 3 right now. What else? Read your textbook. That's it. Study hard. All right. Thank you, everybody. You have a nice weekend. I will see you next Monday. So if you're not going to stay, for office hours, you can leave. And for office hours, we are going to start in 2 minutes. All right, I'm back. So Christina,
Yeah, I'm here.
we'll start from you. So
Okay.
Minchuan's here too.
I'm sorry, what did you say? I can share?
Oh no, I say Minchuan is here too.
Yeah,
So
I
you can.
see that. Okay. So I guess I want to start talking about the logic of, so when we spoke in class, we talked about the logic of the a priori and the sun, but we never talked about them in combination. So I want to, I just want to address, so when you talk about a priori, I know you can use another algorithm, but I'm just going to discuss that one for now. So when you talk about a priori and sun,
Right.
so you're basically, so obviously you're just implementing, more or less implementing a priori in chunks or in partitions.
Right. Yes.
Yes. Okay. So I think some of the confusion, for instance, which I heard other students ask this, and I also asked it on chat, was we kept saying, do we have to use MapReduce? And then we were told we do have to use MapReduce. But when I think the confusion was understanding when and where we use MapReduce as far as MapReduce functions versus MapReduce, I guess, framework, where you're actually just using Python half the time or more than half the time, right? And then using MapReduce, the actual functions, very little of the time. For instance, Ming Cheng had one command, he said, and I had like 4 calls to MapReduce. So that was a little bit of the confusion as far as how you were supposed to implement MapReduce. But, and I know a student asked you that also, Yao Yi, in class or after hours. I heard a student ask you that, and I think that's what we were trying to get a hold of, is figure out, well, how do we combine, you know,
Okay.
MapReduce and anyway, okay.
I think that it
Okay,
was
so
because I was asking you about the MapReduce and the Python function last time.
okay.
Correct. And I was asking you why, like, I mean, you couldn't really tell me anything, it didn't sound like, but apparently it sounds like I was doing it wrong. And yeah, so which I'm just
Okay, yeah. Let me tell you guys. So MapReduce, if we look at MapReduce, this is a framework,
right.
which means this is a programming model. It's not tied to a specific function. It's just the way you code. And the way you use Spark with all these map and reduce functions help you to do parallelization. So for example, when you have a large file, and let's say we want to count stuff, right? If you want to do parallelization and you want to do some algorithm, you want to have one function count here and one function count here. Are we good so far?
What do you mean
So-
count? I'm sorry, what, I'm not clear on the count here.
So this is a priority running here, and this is a priority running for another. Oh, okay. So this is might be a good example.
Oh, okay, because are you displaying partitions or,
Okay, yeah. So this is the input file.
okay,
And in the input file, if you just run a priority, that means you're going to read the entire data from the beginning to the end in one pass. And then you do another pass, reading the data from beginning to the end, right?
you're right.
So no map reduce, no parallelization, just a priority. And we talk about SUN algorithm. And the algorithm itself has nothing to do with map reduce. The algorithm itself just tell you that you can split the input data. You can run a priority here. You can run a priority here at
Yep.
the same time,
Yep, I'm clear on, yeah. I
generate result and combine them, right?
get that, yes.
So to be able to do this in Python or in any programming language, say Java,
Right,
you want to run this in parallel, it's very difficult. That means you have to spawn a thread to process the first part of
Yep.
the file. You
Yep.
have to spawn another thread to process this.
right,
However, there is a way in PySpark to use MapReduce function and do this very easily. Well, I say easy, I mean, you can write the code very easily, but if you don't, if you just start to work on this, it might be difficult, like you guys right now working on assignment 2. But once you get a hang on this, it's much easier than using multi-thread. So in the PySpark MapReduce will be, you just issue one command. I'm not really talking about the specific function in PySpark. I'm saying that you only implement this once, and you say, all right, when you look at the input here, and I want the PySpark or the Spark to run this algorithm on the entire file, but I want you to split it into multiple partitions and parallelize it. And Spark will do that automatically for you.
Right, you're talking about with map partition,
Could be.
okay.
I'm not sure how to link this to the implementation.
Yeah, well, okay, yeah, but I do, I mean, I understand everything you're saying, but yeah, I think that's where the confusion is the implementation. And I remember like, it was either Zune or Zion who was on the office hours and who was asking the same question because he was confused about the implementation. And where I got tripped up is, you're going to have to be bouncing back and forth. Well, in my case, apparently I was bouncing too much, but you have to go out, you do a map partition, go out to Python, and then you bring it all back to group it together back in MapReduce. But what was unclear is, how often do you have to bring it back together? And how much can you do outside? Like, for instance, is there a particular order to doing things? And it sounds like the order can be many different ways.
Right. So first, the order can be many different ways. And second, I don't think you need to bounce back to Python. You can do everything. You can count it, you can collect it, and you can do the second pass all in PySpark.
But how? But you can't, but remember when the student asked you after class, though, you have to do the for loops and things like that out in Python, don't you? I can't, sorry, I can't hear you. Mm-mm. You can't, no. Can you hear me? I can't hear you. Uh-uh.
I think it's his microphone.
Yeah, me too. He can hear us though, I think.
Can you hear me now?
Oh yeah, now we can hear you.
Okay.
I think we lost you.
Well, I guess you're talking about specific Python and PySpark functions.
Exactly,
When
yeah,
I say,
yeah.
somehow I cannot hear you guys.
Oh,
Let me try this again, sorry.
okay.
I think I can answer that a little bit.
Yeah, because when, like Ming Cheng, obviously the distinction is asking about MapReduce framework and asking about MapReduce functions.
Yes.
And so I think that's obviously where the confusion comes up, but that's what was very confusing to me as far as how much we can actually, do in Python and not MapReduce. And it seems to me the stuff that I see on the internet, which I know I'm not supposed to copy, but you can't help but see that there's obviously a ton of stuff on the internet.
Yeah,
But
especially every time you try to type one specific.
exactly, yeah, exactly, and some code pops up. But it looks to me like almost all of that code, the bulk of it, is done in Python, not MapReduce.
I think, sorry. So I think, so when I look at your code, I think what you did, I'm not sure because I didn't do it in that way. So I cannot say it cannot reach the final solutions.
Can
But-
you hear us right now?
Yeah, I can hear you guys.
Okay, he's back. Okay, sorry, go ahead, Ming Cheng.
Yeah, but I would say, so when I replied to your Piazza question, I said you're expected to use MapReduce is because I think because this homework asks for song algorithm. I think in the slides and also in textbook, it's written very clearly. So if you remember, song algorithm professor slide, he specifically say there are two phases of MapReduce, and I think it's the best way to do it. But I think you mentioned there are other ways to do it, so I wasn't sure.
Yeah, no, I know. I mean, I'm just saying, like I said, I think there's just confusion between obviously the terminology because there's the framework and then there's the tools. Yeah.
So
So
first,
yeah.
let me say one thing. So first, you can find anything online, and that's okay. As long as you don't copy it, I'm okay.
Well, when you were gone, Yao, Ming Cheng and I were saying that literally, all you have to do is do a search on this, and there's so much code on the web, so it's hard to avoid it. Yeah.
You can easily see that you can also implement the entire song algorithm with very little Spark, right? You can do most of the things in Python, but the problem is if you do that, you will see that the speed will not be as good as using Spark.
Well, what I was saying to Ming Cheng, because of course, again, you can't help but stumble upon the code that's out there, and most all of it that I've seen, they do 80% of it in Python and 10% of in MapReduce. And then even Ming Cheng says and I can see how he said he has one line of MapReduce.
Yeah, it doesn't really matter. So as long as you can parallel process it, if you want to do it right, you use MapReduce or Spark. Let's just say Spark, PySpark functions. If you don't want to be efficient, you can use Python, and sometimes it doesn't matter.
Okay, but wait a second. So, but if Ming Chang did one line of MapReduce, doesn't that imply, Ming Chang, that the bulk of your program is in Python?
Well,
I mean, what do you mean by that? Because everything is Python actually. So
Well, that's fine, but you know what I'm saying, meaning Python commands as opposed to MapReduce commands.
Python commands. So when I do the a priori parts, that is Python, but I mean,
Right.
yeah, but I think to do it, like Professor just said, you do it parallelly. You use the PySpark MapReduce framework to help you.
Right, but not the MapReduce, not the function, like not the functions like we were using in homework 1. I mean, you'll use one line, but not the whole thing like we did in homework 1,
so
right?
if you do MapReduce, one line can do many things. So I'm not sure how long is that line, because it's different from your regular Python, right? You can do
Well, okay, yeah, yeah. So, okay, well, we can move on from this. The reason I wanted to talk about this, focus on this topic, was because you bring up efficiency. So yeah, my Python is, you know, is killing me because it's, no matter what I do, and I now do have one MapReduce. So what I was doing before, I realized, is that I was coming back to MapReduce time and time again to gather the data. But I was thinking, in my mind, I actually thought that you had to develop candidates based on the threshold and also based on the previous frequent, but it's just based on the threshold and the previous candidate.
So I think in Professor's slides or in textbook, they or also people on Piazza mentioned subthreshold. Do you remember that? Do
You
have
mean local threshold?
Yeah.
Oh, yeah, of course I'm using that.
Yeah, so I think there's a way to, just implement a priori algorithm like as a whole, as a function, and just apply it to one partition. I mean, all partitions.
Yes, I modified my entire program to do that, realizing that, you know, I should do the looping and candidates and the 3, 4, 5 and the tuples and the, you know, the combinations and all of that. And I come back to one line in one line of MapReduce where I bring back all the files, the lists back.
Right.
But I mean, my program is, you know, sometimes it's at least 200 and sometimes over, and nothing I do will change that. I have gone.
So did you collect your data very
Yeah.
often?
Yes.
Okay, yeah, that's a problem. You don't want to collect your data.
Oh.
Once you collect your data, it means it's out of this Spark framework, and you're doing it in Python, or you ask Spark to stop. So this MapReduce programming model, or the Spark implementation, is actually taking many of the comments MapReduce. That's why I said one line can have many functions, right? So you take in all these functions and it try to figure out how to do this very efficiently. So maybe it will do the third one first, then combine with the second, and then parallelize the whole thing and do it for you very efficiently. But if let's say, because we can implement this either with or without PySpark, right? The result will be the same. It's just with Python, it would be much slower. So one thing that I see people do would be they would write some MapReduce code. They collect the data. They have some logic, just use Python without Spark. They do some simple calculation, and then you invoke PySpark again. That will make it slow, because now you're collecting data. You do some process, then you ask Spark to do something. Instead, you should ask Spark to do all the things, as many as possible, and it will be able to help you parallelize as much as possible. So
yeah, okay.
Don't collect.
Yeah, but when you say have Spark help you, you mean just by, you launch it through map partition and you're partitioning the data. So is that what you mean as far as Spark helping you?
Right, that's one. So that's parallelization, right? The second thing is when you are doing all these transformations or data collecting, or let's say combiners, you don't really have to implement a combiner in Spark. It will look at the code, it will automatically figure out, hey, we need a combiner. So it will do that for you. So that's why.
But if you're out in Python, it's not going to do that. Once you map partition, then you're out of Spark. Is that correct or no?
Once you collect the data, you're out of Spark.
Yeah, if you're still in map partitions, then you're still in, in Spark in a way. Yeah.
Yeah, but the only time I collect the data, Yaoyi, is after I'm finished and I bring the lists all back.
But I think the way you did it is you sort of implement a priori algorithm. So every step you did a map reduce. So from singleton to pairs and from.
Yeah, I didn't, I reworked all of that. I redid it all.
So
I redid my entire programming chain. So now it's just one line in one map reduce line.
Okay, so
all the bulk of my time is of course in the looping, because loops take time. And specifically in the type of loop you would need, for instance, to take like a 5 tuple and say, okay, this 5 tuple can only be a candidate if the 4 tuples behind it are built into that 5 tuple. That's where all the time, is going, is to that looping.
For that, I think you can do MapReduce.
But how? Because once you go back to MapReduce, then aren't you automatically bringing all your partitions together again? And you don't want to do that, right?
So when you say 5 tuple and you want to figure out if that 5 tuple, if you need to count that 5 tuple, that means you are still working on one partition, right? And that's a parallelized process.
Correct. Yeah.
So if that's a parallelized process, you will need to figure out how to parallelize it.
Well, yeah, I'm parallelizing because I'm parallelizing because I'm out in the partitions. I know I'm parallelizing, and I know when I group it back, when I bring it all back, then I bring all the data back together. So, I mean, I assume that's how you're supposed to do it, right?
Wait, so which part takes a lot of time?
I think obviously, I think it's all the Python looping. Obviously, loops take time, and I think it's the Python.
So the Python looping, what did you do? Where do you need that Python looping?
I need it to do, when you do the candidate, when you go through your candidates, you get your singles, then you have to figure out from those singles, like create all the doubles, but only the doubles that pass the threshold and are composed of the singles. And then you go to the triples, and those have to pass the threshold, and those have to be a triple, for instance, can only be a candidate triple if three two tuples that make it up were also considered.
Right. Yeah, I don't think that would take a lot of time because you do not have that many candidates here. But
well, wait. But what do you mean you don't have many candidates here?
Because when you start to have, when you use a priori, right? When you start to count frequent singles, frequent doubles is probably the most time-consuming part. Then for frequent triples, you don't have that many.
But no. In the review2 file, there are a ton of candidates.
So, Minchen, can you comment on this?
I used to have 30 millions of triple candidates in my memory.
Yeah.
I don't think they're that much. Do you use the samples I put on Piazza and count it? Like count how many tuples? I mean, two tuples in it.
Oh, in review2, you mean?
Review2. So, I mean the sample.
I'm sorry. In small 2, you mean?
I mean the big one. The
Yelp one that I haven't even gotten to yet. The Yelp one.
Oh, so I think small 2. There are not that many. There's no like 30 million.
there's not 30 million, but there's pages and pages, meaning you can't, like if you're trying to,
No, I was talking task 2, the Yelp data.
yeah. Oh,
But, and I found out that there are actually around 200,000 triples.
But so you guys are saying that you already parallelize this function to find candidates, but it's still very slow?
yes, Mike. Xian, do you have a slowness problem as well?
I have already submitted my homework.
Oh, okay, sorry. Well, I have to assume a lot of people have it because there were only 20 people in the lecture today, so.
Well, usually Wednesday, we don't have that many people.
Oh, okay.
How do you solve it, Xiang?
Well, I actually changed my way of generating the larger item set of candidates. For example, if I have a set of tuple that are frequent, and then I would put frequent singles in the function, and the list of, hold on one second, I'm a little bit messy.
Did you do it the way when you were talking on the office hours when the girl was saying that the ones that weren't actually in the set would fall out because of the local threshold?
Yeah, kind of like that.
Yeah, I was wondering, I almost took that approach. I'm not sure if it would be better for my time or not, but yeah.
It works. It looks like it works.
I don't know. Xian, is your time close or is it like really, really good?
I think at least it is not that bad. My time was on the task 2 Yelp data set, 40 seconds.
Yeah, normally that's the case. I mean,
Oh my gosh, geez, really?
Yeah, because I realized that I did two very wrong steps. One is keeping so many things in the memory, like the professor said, because I used to keep both my candidates and my frequent, but I realized that frequent matters and candidates don't.
I mean, technically, like, I mean, Yao Yi, although you made a point about the memory and the issues, technically, when you do map reduce functions, it runs, like you're saying, it runs much faster. Like it'd be easier just to use, I mean, when you're already out there gathering the candidates, you're already going through every single one. So you might as well bring back the numbers for the frequent pairs because you're already going through every one of them.
Yeah, but this is too much detail for me to be able to help you because I haven't implemented this for years.
Yeah.
But I can tell you this: whenever you need to use, whenever it's parallelizable, you should use Spark. And I can see this is a wonderful discussion between you guys.
Well, can I just say that the assignment's hard enough without having to do the computational efficiency part?
Well, yeah, no, because count stuff is very easy.
I don't.
Right? So the whole thing about this is because I know very little. You guys have very little experience with Spark or zero experience, right? So that's why this second homework is actually not easy because we need to be able, you need to be able to know when you need to use it, like why you don't want to collect and how you should use it combined with your regular Python.
I'm actually quite comfortable with Spark more so. I think my issue is not being able to be efficient enough in Python because of all the Python code we're using for the,
Right.
yeah.
But for that part, you will need to consider if you can use Spark for those parts too.
But can't you only use Spark if you weren't out in partitions? Don't you have, if you use Spark, wouldn't that require bringing the partitions together again?
Well, I cannot really answer that question. This is too long, but there should be a way that you will be able to do this. But I highly recommend you guys work together.
Yeah, well, I'll keep asking Ming Cheng questions, I guess. I I guess I just don't, everything that I see out in the internet, all the algorithms, I don't even understand how Xian can get it going that fast because of that comparison you have to make between 5 tuples and 4 tuples and 4 tuples and 3 tuples and 6 tuples and 5 tuples.
Well, actually, you can just try to do it on regular Python. If you copy those, if you use Spark to generate a frequent single item set, right? You can store it in another Python file to do it as a regular Python file, and then just try to keep doing this. And
Yeah, I know. I can pull my files back and forth real easily. Like I'm comfortable with that with Spark and Python, but it's the part about the looping where you have to take, like, just a small example. So a 3 tuple can only be a candidate if it passes a local threshold. And also you have to make sure that 3 doubles in the set before that were candidates to be able to justify using the triple as a candidate. And that's kind of a little complicated process to program.
well, can I talk about pseudocode, something like that?
Sure. We don't have to do it right now. And Run has a very good question. Why not just use PCY? I guess because a priori is easier to implement. So most of
Yeah,
priori.
true.
Is PCY, do you get into the bitmaps and stuff?
Yeah.
I mean, I was telling you, I read an interesting paper on an implementation that I haven't tried, but an interesting paper that suggested that it worked very well to actually start with the largest tuple and go backwards.
Mm.
So,
Yeah, that sounds pretty cool.
yeah, but I can't, the time of, is the homework number 3, are we requiring computational efficiency as well?
I'm pretty sure every homework requires this.
Except homework number 1.
Yeah, because if there's no time limit, it's just too easy. It's just implementing counting stuff and comparing vectors. That's probably undergrad Python assignments, right? And these are useful skills. So I highly recommend you guys to find. I do have on Piazza for you guys to search for teammates.
I know, but I think some people might, I mean, I know myself personally, I think sometimes that actually causes more time, not less time. So I don't know. It depends on how well, it works out. And everybody's timelines are so different, right?
Yeah.
Yeah, usually I saw when we were on campus, like every couple of days before the assignment due date, library full of data mining people are sitting there and discussing algorithms.
Interesting. Yeah, interesting. Yeah, I guess it's maybe a little more challenging to do it online, but yeah.
I can also do office hour just for you guys. Anybody who like to join, and I will not be there, but you guys can come.
Yeah, that's a good idea, maybe. Yeah. I guess Ming Cheng or Xian, do you have any suggestions for me as far as making my Python more efficient? Because I'm not sure what else to do except trying a whole different algorithmic approach.
I would say this. Maybe you can schedule a time to talk to Minchen. I know Minchen is busy until Thursday night. So maybe Friday you guys can meet for some time and he will be able to look at your code quickly.
I'll be going on day 3 of my extension, so I'm not sure how much I want to use.
Yeah, I will give you one more day because this is not your fault. Because Thursday, I don't want Minchen to spend time because Minchen has a test. I want him to focus on the test tomorrow. Okay. So that's okay. I'll give you one more day.
Okay, thank you. Yeah, does that work, Ming Cheng, for Friday?
Right. So I think Xian just provided a very good so I think you can try that first and see if you really need. And also even if we scheduled a another office hour, I still can give you more like conceptual ideas. So not like to not to, so to be fair with other students, I cannot expose too much of.
Well, I know, but I mean, I guess moving forward, what are you able to expose? Because
Yeah, so here's what I can say. So Minchen, as long as you don't share code with Christina, you're okay. So one way that we can do is, Christina, you can show your code to Minchen, but I know reading other people's code is not very efficient. It will be terribly time consuming, but maybe you guys can schedule a time for 30 minutes. And what he can do is he can look at your code quickly and say, all right, I think this part you should do Spark, and this part is the most time consuming part. And maybe he can show you a couple ways that you can time your different part of your algorithm, right? Without telling you how to do it. But I think conceptual wise, we are talking about the algorithm. We are all past that algorithm part. Now is the implementation, right? Implementation, you are having trouble. So Minchen, if you can look at the code and say, all right, you shouldn't do this. This is not okay. And this will be very slow. And another solution is just point Christina to the maybe some online code or online. It's totally fine as long as the code is not the same.
yeah, and I frankly, like I said, it's kind of hard, obviously, not to look, but frankly, anything I've seen is not dramatically different than what I'm doing. And that's why I can't, that's
Oh,
why,
yeah.
yeah.
Don't trust them.
That's
Right.
true. I guess you never know. That's true. You never know.
Yeah.
But can I ask you one more question, Yayu, about the actual algorithmic part?
Yeah.
So when you're doing Sun and you divide it into partitions,
Right.
and you're finding the local thresholds, but then you're also, again, doing this 4 tuple, 5 tuple, et cetera, to make sure that they're monotonicity, right? Monotonicity. Again, is it just an issue of memory? Because when you're out there in these two partitions doing all that work, and then you need to come back and go out again to get the frequency, it seems like, what does that save you? What does it really save you?
Yeah. So you can actually keep the counts, right? And then you can do one pass. Once you keep the counts in the reduced phase, you just add up all the counts and you will be able to.
That's actually how I was approaching it initially.
Right. But the problem is a counter is actually very expensive to keep.
Oh, right.
So instead of using a counter, you can just say frequent or not frequent.
So really, Sun is not necessarily a time saver. It's a memory saver.
Well, it depends on how you look at it, right? So memory saver usually equal to time saver when you have large, very, very, very large data set.
Okay. Fair enough. Yeah. I think that's one thing that threw me, though, because when I was out there doing it, I'm thinking, well, why don't I just grab the counts? I'm here already. I mean, why don't I just grab the count?
Yeah, if you don't work, if you never have to handle large data set, sometimes it's just. So I don't know if you guys know this Amazon Snowmobile. They have to. It's a service that they will drive a truck to your place and pack your data in hard drives and go back to the data center and upload it. Right? But if you don't have that type of amount of data, you will say, oh, why not just transmit it over the internet, right? But for that amount of data, it would take you years to transmit it over the internet. So it's just a problem of scales.
Okay. But is it also safe to say that when you're counting whether or not it meets the localized threshold, once it hits the localized threshold, there's no reason to count anymore, right? A particular item. So that's probably a good practice if you can implement it, of course. Right. Okay.
All right.
Yeah, thank you. Thanks for your time, and everyone's Mingcheng and Zion. Thank you. Yeah.
All right. Thank you. Thank you, Minchen.
Yeah.
All right. So who else has questions?
I have some questions about the MinHash and the LSH. And
Okay.
can I share my screen?
Yes, of course.
Okay, perfect. So basically, this is the full steps of finding similar documents, right?
Right.
Okay, and so for the I have some specific questions about each steps. So for step 1, and we initially construct to compare the different documents, and we change documents, use key shingles to change documents into assets, right?
Right.
And so let me see. And so my first question is that element A, B, C, D means the shingles?
Yeah, those are the shingles.
Oh, there are shingles, and the signature means that if shingle 1 in the document 1, and it will record 1, otherwise it will record 0.
Exactly.
Okay, perfect. So and we change the shingles into the different integers, and then build the like
Yeah, because integers are usually IDs that is easier to handle.
like this one, right?
Right. Exactly. Yeah.
Okay, so from the left to the right, it is the build the min hash signature of length n, right?
Right.
So this is step 2.
Yes.
Okay, and so actually, if we want to build a length n of min hash signature matrix, do we need? So that means we need many different hash functions.
Yeah.
Okay, got it. So just like many different hash functions, if I want to build length of 100, and we need 100 different hash functions.
Yes.
Okay, got it. And the so
Yeah.
for step 3, and we need to choose the B and R first to adjust the threshold to meet the just like to reduce the FP and the FN as much as
So
possible.
remember what I said in class. You usually have an application defined threshold. Very often you want to say, I want to find similar documents with similarity larger than 80%, right? And then you have that, you adjust your predict threshold, you use your BNR to adjust that predicted threshold to match your application threshold.
Yeah, yes,
Be able
yes.
to do it.
Okay. So, and after we got B and R, and then we like go back to wait a minute.
Wait, Professor, you have a similarity threshold first, right? And then you pick your BNR based on what you want the probability to be?
Exactly, yes.
So for this page, we use min hash change from the characteristic matrix to the signatures, right?
Okay.
Yes, and then we come to this part, and we use we already have B and R, so we already divide the whole.
Let me clarify that again. So
Okay.
here you have, this is that function, right? This is your
Yes.
car, this is your probability.
Yes.
And you very often will define your application threshold first. And
yes.
this function has a predicted threshold here. Okay, this is the part where this curve rise at midpoint. And the practice is you want to adjust this predict threshold to match this application defined threshold so that you will be able to better look at your false positive and false negative rate, because they will be just here.
And the predicted threshold is the probability threshold. When you
Yeah,
say
it's just here. It's where this probability has 0.5.
yeah.
Please define this.
Well, my question is that do we decide or choose the B and R first, or we
Application threshold first. Use your B and R.
or
Match that predicted threshold to the application threshold.
application threshold first.
Right.
Yeah, the similarity threshold.
The similarity you want.
Yeah.
I know this is a bit different from the slides because the slides doesn't really talk about the application threshold.
Wait a minute. So in step 3, we need to. So is that based on the functions you told in class to calculate the B and R?
No, here, this says choose B and R to adjust the predicted threshold.
Yes.
What it doesn't say is to adjust the predicted threshold to match your application threshold because you have a defined application threshold.
Yeah, right. Those tables you provided.
Right.
Oh, okay. So after we have.
No, I don't. So are you sure you understand? So let's say this is your curve, right? And when you
Yes.
have a curve, you will have this curve is decided by B and R.
Yes,
right?
yes, yes.
And this curve also decide on the predicted threshold. This is where the prediction is 0.5, and there will be a Jaccard similarity here. Okay, let's call this 0.6 Jaccard similarity. But for your application, you might not want to use 0.6 because you want to find all the documents that are 0.8 similar,
Yes.
80% similar. So
Yes.
what you will then need to do is to adjust this B and R so that you can push this predict threshold to here. So your line might be looking like this, right? If you change
okay,
B and
okay.
R, you will change this. So that's
Okay.
what this means.
Okay, got it. And after we already got B and R, and then we go to construct the candidate pairs, right?
Right.
Like for each band we have independent hash functions, and then we if they hash if they have the hash same value, and then they will be the candidate pairs.
Right, right, but they don't have to be independent because you're
Yeah.
going to hash each band separately. So
Yes, got it. Yeah, and after we have after we construct the candidate pairs, and then we like, and then just like to calculate just like this.
Oh, once you have candidate pairs, you have a couple options, right? You can use the signature to estimate the similarity, or you can go back to the original data to calculate the Jaccard similarity. It all depends on if you have enough resource to do this.
Okay, so just like after we have candidate pairs, and there are many ways to find the truly signatures, right?
Right.
Okay.
So that's here, right? So you may check the documents. It doesn't say using the original, but it's using the original set if the signature are similar. So if the estimate similarity is high, you might want to check something like that.
Okay, got it. Okay, thank you. And my next question is about today's lecture. Yeah, I'm a little bit confused about this prediction part. So I actually want to compare the page 21 to the I want to compare those two different examples. So for this example, we need to predict the question mark, the value of question mark here.
Right.
Sorry.
Right.
Okay, and then we need to compare U1 to U4 and U5 because only those two users have the value of I2?
No, you compare U1 to U2, U1 to U4, U1 to U5.
How to decide this? Because
Everyone that has rated.
okay, so except U3 because U3 do not have value here.
Right.
And then we can use functions to predict the I2, right?
Yes.
Okay, so and for these examples, we need to compare different movies.
Right.
Okay, and
This is item to item, right? So for user 5, you want to guess the rating for item 1. You want to know how similar is item 1 to all other items that user
Okay.
5 has rated. So that will be here.
So in which case we will compare the column 1, 3, 5.
That's the
9.
user based.
Huh?
That's the user based.
Oh, user based. Okay. So this is item based, and then we will compare a column by row by row.
Right.
Okay, got
So
it.
the idea is actually quite easy. If you work on some exercise on the textbook or do the exercise on the slides, you will be able to figure this out. So I forgot to mention this. Next week's quiz, I will ask you guys to do this as an exercise, just to make sure everyone will try this.
Okay.
So can you do me a favor? Just post it on Piazza, say, in case people didn't watch till the end of the video, I want them to know that we are going to have this on the quiz.
Have this one on the quiz?
We're going to have item CF and user-based CF on the quiz. Not exactly the same example, but I will ask you guys to do the prediction on the quiz.
Okay, got it. I think I asked a very important question.
Okay.
Okay, got it. So thank you very much. I think I do not have.
This is a very common interview question if you're interviewing for local people who are building recommendation systems.
Okay.
So you want to do it right.
Okay. Got it. So actually, this is a very important, crucial steps for recommendations. Okay. Thank you very much.
Sure.
Yaoyi, I guess as long as we're on the topic, on the quiz for that last question, was that question kind of phrased in a different way than what you've been presenting in lecture?
Which question?
The one where you're comparing, instead of comparing documents to each other, you're comparing all the documents to an outside document that's not.
Right. Yeah, it's a little bit different setting, but it's the same method.
So it's kind of the same logic, more or less.
Right.
Okay. I wrote Ming Chang because I wasn't clear if he was suggesting that he could see me on Friday or not. Were you clear?
Yeah, I'm not sure, but I will send him an email too. I will make sure he knows what are the things he can say to you and what are the things he cannot say.
Yeah.
But I think most of the things are a free game. As long as he doesn't show you the code he wrote or a correct solution, or as long as he doesn't spend too much time helping you debugging, I think that's okay.
Okay.
Right? So if he can point out some sections that would need improvement, and point you to a resource and tell you how to improve it,
yeah,
I think that's
well,
fair.
that would be great, actually. When he went off, I just wrote him a quick email too. He had said that either Zun or Xian left something that was helpful. Was he just talking about the PCY suggestion?
No, I don't think he's talking about PCY. I think he's talking about the way to prevent things in the from storing in the memory and all the tricks that Zun was doing. So
well, whatever trick Zun was doing, you mean?
Yeah, I don't think it's BCY.
Okay, well, do you have any, I'm a bit concerned, like, because this has had me up, till 2 and 3 in the morning every night. I'm a bit concerned about my, I can make a program work, but efficiency is a whole nother deal.
Right.
And do you have any suggestions as far as resources or readings that where you can improve that? Because I often feel that I probably take a really greedy approach to my programming. And yeah,
I think look at examples would help. Like you
Yeah.
said, finding examples online,
yeah,
but ignore those with Pythons only. Focus more on how people use. That's why I said if you know how to do Scala and look at Scala code, that'll be very helpful, right? So that will prevent you to do too much hurdles.
yeah. I was really looking forward to doing Scala, but I'm thinking I'm not going to get to that part again. So,
Right, it might take too much time. Yeah, I understand that.
yeah, okay. Okay, well, thank you very much for this evening. I appreciate it.
Sure. So assignment 1 will be a little bit more challenging than this one, but 4, 5, 6 should be okay. Once you get through all this process, you should be okay. So
You mean assignment 3, right?
but assignment 3 will be more challenging, but 4, 5, 6 will not be that challenging. 1, because you already know how to do this from your assignment 1 to 3. 6,
Okay.
they are not that demanding because I want you to be able to spend more time thinking about how you would improve your assignment 3 because that's your final project.
Okay, that's great. That's good to know. And it's also actually kind of a relief because like you were saying, we actually have we have a pretty good buffer of time on assignment 3.
Right.
Yeah.
But I will say this again, make sure I highly recommend you to find people to work together.
Well,
I say this to every people, not just you.
Well, I have, I'm in CS 590, because I'm in my last semester. So I'm
You're
in,
taking 2 courses?
well, CS 590 is the one that you can get 1 or 2 units and you're working with like an outside, kind of a startup type situation
Okay.
company. And it just so happens they're focused on a product that's based on Yelp. So it's good. It kind of,
Okay, yeah, that's nice.
yeah, it's nice. They're doing sentiment analysis, like natural language processing stuff. Anyway, the guy chose me to be the team lead because I've been around for a long time. So, but the kids, I call them kids because I'm older than they are. So, the ones that I lead, all of them have taken 553 and have offered to help me if I need it.
Yeah, exactly, right? So it's collaboration. I don't think it's really difficult to do this by yourself.
I mean, I don't want them to they can tell me code, but of course I don't want that. I really want to I want to figure out how to think of it in the right way myself.
But maybe
So,
sometimes you only need some pointers.
yeah,
That'll get you a really quick start. Right?
Yeah,
You
true,
don't want to be
true.
stuck somewhere for too long.
Yeah, true. Okay. Yeah, fair enough. Yeah. Okay. Thank you.
All right. Any
Okay.
more questions? So Chenyo, do you have questions? No. Okay. All right. I guess you just stay here to listen to us. All right. Thank you, everyone. Have a good
Okay.
night. I'll see you next week.
Okay.
All
Bye.
right, bye.